In this video, we'll be talking about quadric surfaces. I wanted to begin by mentioning their two-dimensional analog, which are these conic sections. So first of all, conic sections, they can be written in this general form, although this is a bit harder to identify what the conic section is. You'll more commonly see them in one of these three forms, where you have fractions, like so. A and B actually have meaning for both the ellipse and the hyperbola. They're based how far the ellipse or hyperbola is in the x and y directions stretched for the ellipse. For the hyperbola, it's about a bounding box that you can construct from the uh, it's a bounding box that is based on the asymptotes and parabola. I think we're all familiar with parabolas, so very good. Now quadric surfaces. So similarly, a quadric surface, we have a lot more terms because we go up a dimension. So we allow ourselves a CZ squared term, and then we have each of these, which are the different ways of picking two different variables, so x, y, xz, and yz, and then the individual single variables, x, y, and z, and then plus a constant, okay? And that's all of the things that you can do as long as you keep the exponent 2 or less, and you are in three-dimensional space, so you have three variables to work with, then everything is going to be of this form. Right? That's the most general form you can make of everything. And the specific conic sections that show up are these six, which I've pulled the graphics from the textbook. So you have this ellipsoid. You see that you've got the x squared over a squared plus y squared over b squared plus c squared. Z squared over c squared is equal to 1. You can always normalize things to get 1 on the right-hand side, so by just dividing appropriately. And you'll see that this is the ellipsoid. I think one thing I want to mention, just because I'm going to immediately start talking about this is the idea of a trace. So with analyzing objects that live in three-dimensional space, a useful thing to do is to intersect that object with a plane. Typically, the planes will be parallel to one of the coordinate planes, so the xy, xz, yz planes. And when you do that, you end up with a two-dimensional, an object sitting in two-dimensional space. It'll be a one-dimensional object, so it'll actually be one of these conic sections. So what I was immediately trying to say was actually that the traces of this ellipsoid are all ellipses. If we intersect it with the xy plane, all three of the planes actually, xy, xz, or yz planes, you end up with ellipses as your traces for this ellipsoid. So, or for any ellipsoid for that matter. The next one, a one-sheet hyperboloid. So notice that in this shape, the shape is connected. So let's immediately contrast the one-sheet hyperboloid with the two-sheet hyperboloid. And you can see that in this situation, they are not connected. And so this is called a two-sheet hyperboloid. Now let's take a look at how the formulas differ. So notice that with the hyperboloid, and maybe we can compare this against the formula for the ellipsoid, there's a negative here. Right, this negative is the important part. Perhaps I can, what's a good color? I can circle that, right? And to contrast the one-sheet hyperboloid with the two-sheet hyperboloid, notice that there are two negatives. Again, what we do is we can normalize it so that the right-hand side is the constant 1. Okay. So the fact that there's just one negative sign, you get the one-sheet hyperboloid, and when there's two negatives, you get the two-sheet hyperboloid. You can also notice that the direction is can show up in the formula. So the negative being here, you see that there's like an axis of symmetry, which is the z-axis in this picture, and same with this, the z-axis in this picture, and it has to do with the sign. So if the signs were different, like in this case, if the negative was in front of the y squared instead of the z squared, then the axis of symmetry would be in the y direction. Yeah. And a very natural thing I want to actually mention is that these two are closely related through the elliptic cone, actually. So notice with the elliptic cone, instead of 1, you have 0. And so that is basically a degenerated version of these two. So if you can imagine, and maybe it'll be better if I just simply show you. Let me try to pull up the animation that I had. So what you can do is you can actually modify that parameter on the right-hand side. And if you do that, then the picture changes. So it kind of warps. So you can see that this is very pixelated down or smoothed down, but it can eventually change, and then it passes to once it crosses 0, you switch from the 2-sheet hyperboloid to the 1-sheet hyperboloid, or the other way around. And so the generated version of this is the elliptic cone. Let's talk about traces. I forgot to mention that. So with the 1-sheet hyperboloid, let's see. If we intersect with the xz plane, we get hyperboloid. If we intersect in the yz plane, it's still a hyperboloid. If we intersect with the xy plane, we should get an ellipse. I've been saying hyperboloid. It's hyperbola. The intersected versions are hyperbolas and ellipses. And the same happens with the 2-sheet hyperboloid. The intersections with the xz plane and yz plane are going to be hyperbolas, and the intersection with the xy plane will be ellipses. With the cone, the same holds true. It's just that if you, say, intersect with the xz plane, what you get is a degenerate hyperbola. The hyperbolas also behave in the same way, in fact. So you have hyperbolas that look like this, you have hyperbolas that look like this, and they cross through the hyperbola that looks like this. You can imagine that some other parameter that gets, as you change it, it gets pointier until it gets to this kind of a intersection, and then it opens up the other way around. So yeah, this cross is actually a degenerate hyperbola, right? And now these last two quadric surfaces, so these are paraboloids, and their name comes from one of the traces that you can find. So in this case, the trace that you get if you intersect with the xz plane is a parabola, but if you intersect with the xy plane, you get an ellipse. So it's an elliptic paraboloid. Whereas here, if we intersect with the xy plane, we would get hyperbolas. And so, but the xy, not xy, the xz and the yz planes, if we intersect with those, we would get parabolas. So this is a hyperbolic paraboloid. And again, notice the sign difference here. So with the plus, it's a elliptic. With the minus, it's hyperbolic. Yeah, and also the fact that one of the variables does not have a square in front of it. So that makes it so that you don't have... so this can be described as a function rather than any of the other four. The other four, they aren't describable as functions because like you have a positive part and a negative part, all coming from the fact that all three of the variables are squared. So there's that. Okay. Another thing to mention, just a useful thing for you to know about is that there's software that you can use to graph these kinds of things in three-dimensional space. And the one that I can probably recommend is this. So if you actually download the file, you can click on the link, but I think Canvas doesn't allow you to just immediately click on this link, but in the PDF it is hyperlinked. So if you click on it, you'll reach this page, and now let me just explain how you work with this tool. So it has a lot of functionality, and I certainly don't know all of it, but I do know at least this. These kinds of shapes are called implicit surfaces. Um, so what you can do to graph these kinds of quadric surfaces is you add to graph and then hit implicit surface, and I'm going to untick that and tick that instead. And well, here you see this is a one sheet hyperboloid. Yeah, and you can modify the equation here. So if I put another minus instead, then we get the two sheet hyperboloid. If I want to change the dimensions of this, let's say to make what looks like the x. If I make the x larger, I can see a bit more of it. So that's nice. Yeah, and the reason, like, this is called implicit because we're not solving any of the variables to make it into a function of one variable, like in terms of other variables. So that's what the word implicit means. Okay. I guess coming back to the document. So let's talk about some example problems. So this one is given a graph of a quadric surface, specify the name of the quadric surface, and identify its axis of symmetry. So a lot of the problems of this section are just to do with identifying your surface and maybe doing some algebra to get your the equation defining the surface into a form that you can recognize. Right. So here, let's see. Well, clearly this has a vertex right there. So this is a elliptic cone, right? Just like that. We're not given an equation in this case. We just have to identify it based off the picture. So it's an elliptic cone, and the axis of symmetry, you can see that the symmetry is going in this direction. So the axis of symmetry is the x-axis. So you might also be given an equation that describes a quadric surface, and if you aren't given any software to do anything, then you would have to just analyze it based off of whether it looks like any of the 6 equations here. And so the thing to do is to make it closer in form. So what we can do is divide by 10 in this equation. And so doing that will get this form. And so notice like A, B, and C would be what we would call these things in the denominator. And there are signs here. So you have one positive sign, 2 negative signs, which matches this case, the two-sheet hyperboloid, which is what I mentioned there. And then the axis of symmetry is the odd one out, I believe. Yeah. Yes. Yes. It actually works for both one sheet and two sheet. It's the odd one out. So yeah, there we go with that. And the last exercise we have here is this one. So basically, we just have a more involved form. So notice that what happened here is we didn't have all these complicated terms, so it was really easy to convert it back into a form that we can identify. But in general, we might have all of these terms. So how do we deal with that? Well, the process we use is we complete the square. Well, if you have mixed variable terms, you have to do a variable transformation. But I don't think that we talk about that. At least I didn't see that in your problems. So imagining we don't have those cross terms, those xy, xz, yz terms. If we just have x squared, y squared, z squared, and x, y, z, and a constant term, the process that we can use is completing the square. So let's go through this slowly. So what you want to do is group things up into the same variable. So I noticed that I have an x squared and a minus 6x. Okay, so I would group those, and I wouldn't figure out this 9 just yet, but I guess we can figure it out right away. So from the x squared and the minus 6x, you then can conclude that this term needs to be 9. in order to make it a perfect square. Oh, I had to fix that typo. That should be a square there. Yeah, but so the way you recognize it is this last term should always be this term divided by 2. So you're always going to have, it should look like ax squared plus 2a plus a squared is equal to x plus a quantity squared. This is the idea behind completing the square. So the middle term, you divide it by 2, and then that's the term that you would get after you've rewritten this as a binomial squared. But the actual value that we need to add, that we need to modify our initial expression by, is the quantity a squared. So we notice that we have to add 9, and then we end up adding 9 to the other side as well. So I do that, and I do that with the other two terms also. So grouping the y's together, we have the 4y squared and the minus 16y, and then I factor out the 4 just to make it easier to complete the square. So by factoring out the 4, I would see a y squared minus 4y, and then to complete the square, I would have to add 4, but in parentheses, which means that outside of the parentheses, what we've actually added is 16. So I have to add by 16. And then grouping the z's together, we have a minus 4z squared minus 16z, which when we factor the 4 out, we would get a minus 4 times z squared plus 4z. And then to complete the square, we plus 4. And so that means that we've actually added negative 4. Notice you have to distribute the negative to that final term. So that ends up adding a negative 4. And so simplifying this, again, this should be a 2 there. Get rid of that. So you actually have a x minus 3 quantity squared plus 4 times y minus 2 quantity squared minus 4z plus 2 quantity squared is equal to 4. That is one step closer to being something we can put into like the standard form for a quadratic equation. Okay, well, whatever. Lastly, divide by 4 to get this side to be 1. That's a lot of the forms have 1 on one side. So when we do that, we get this form. 4s cancel out quite nicely in those two terms. We still have a 4 there. That's fine. And so this looks like one of the hyperboloids. I guess I would not have this memorized, but it's possible to. Just one negative means that it's a one-sheeted hyperboloid, and where am I? One-sheeted hyperboloid, and the odd one out is the axis of symmetry. So it's the z-axis of symmetry, and the center is something we can identify as well. So that's how much we've offset the x, y, and z. So we've offset x by 3, y by 2, and z by negative 2. So the center is 3, 2, negative 2. And that's all I've got.